Hello, everyone. Welcome back to the GOCC. This week, we'll have Melanie Ferrari talking about bijections for generalized Wilf equivalences via inclusion-exclusion. But before I let her go, I would like to remind everyone of our community statement. So the GOCC is a seminar for graduate students by graduate students, and our community statement on our website has three main principles. First, we are all learning. Secondly, everyone has something to contribute. And three, no one has all the answers, and that includes the speaker. So without further ado, Melanie, take it away.
Thanks. Okay, so I'll be talking about bijections for generalized Wilf equivalences. And so this is a project that I'm currently working on. It's a work in progress, and it's something I've been doing with my advisor, Peter Doyle. So I'm going to start off by talking about some definitions. So we'll cover inversion sequences and patterns, and then we'll talk about Wilf equivalence classes or inversion sequences. And then we'll talk about how to show those equivalences using bijections, and you can do this directly, or some of the equivalences you have to prove via inclusion-exclusion. Well, in the thesis that I was studying this from, they prove it via inclusion-exclusion, but we show that you can follow through those maps to actually compute directly a bijective proof for some of the equivalences. So the first topic is inversion sequences and patterns. So first off, we're going to note by Sn the symmetric group, and we're going to consider permutations in Sn in one-line notation. So an inversion is a pair ij where I is less than j and pi I is greater than pi j. So it's a pair of indices where the elements are out of order. So for example, if the permutation is 1, 2, 3, 4, every element is in order, and so there are no inversions there. But 1, 4, 2, 3, 4 and 2 are out of order, so we have an inversion at 2, 3, and also 4 and 3 are out of order, so we have an inversion at 2, 4. And an inversion sequence is just any integer sequence satisfying the condition that the ith entry is between 0 and I for all I less than n. And we let I sub n be the set of inversion sequences of length n. So for example, 0, 0, 1, 0, 2 is an inversion sequence because it satisfies this condition. And we can represent inversion sequences by under diagonal lattice paths. So if you wanted to draw this one, then you could draw the zeros, and then the 1 would be at height 1, and then the next 0, and then the 2 would be at height 2, and then you could connect them like this, and you would have like an under diagonal lattice path. So inversion sequences are in bijection with permutations. So if you have a permutation pi and Sn, you can compute its inversion sequence by basically the ith entry of the inversion sequence is going to be the number of elements to the left of I that are greater than the element in position I. So for example, if everything's in order, 1 has nothing inverting it, so we have 0, and then 2 is greater than everything to its left, so we have 0, and so on. If everything is decreasing, so this is like completely out of order, we always start with 0 because there's nothing to the left of 8, and then 7 is inverted by 8, and 6 is inverted by 8 and 7, and 5 is inverted by the 3 things before it, and so we get this sequence. And then this one is just kind of like a random sequence. So if we compute for 3, there's nothing to the left, so we get 0. For 5, 5 is greater than 3, so again 0. 4 is less than 5, so we have 1 there. 1 is less than everything before it, so we have 3 there. And then 7 and 8 are greater than everything before them, so we have zeros. 2 is less than the preceding. Oh, this should actually be 5 because 2 is less than everything but 1 here. So this should be 5. And then 6 is inverted by 7 and 8, so that should be 2. So if you add up all of the terms, all of the elements in this sequence, you will get all of the inversions of the permutation pi. sorry, I'm clearing my annotation. Okay. So a pattern is a sequence where the ith term of the ith term of this pattern is between 0 and r-1, where r-1 is the number of elements in the sequence. And we require that the element j can only appear in a pattern if j-1 also appears. And then also, if we take a word over the integers, we can define its reduction to be the word given by replacing all occurrences of the ith smallest entry by i-1 for all I. So for example, 0, 1, 1 is a pattern because it satisfies these conditions, and 0, 3, 3 is not a pattern because 3 appears, but 2 does not. And also, I guess it doesn't satisfy this because the length is 3, and so you want the things to be from 0 to 2 here. So with 0, 3, 3, it doesn't count as a pattern, but if I reduce it, if I consider 0, 3, 3 as a word, and I take the reduction, I get 0, 1, 1. And we say that a sequence contains the pattern P if it has a subsequence which reduces to P. And if it doesn't contain P, then it avoids P. And we'll use INP to denote the set of inversion sequences of length n which avoid P. So you might have seen, like, for permutations, you can talk about patterns for those. And in inversion sequences, you can talk about patterns which have more than one repeated entry, because the entries in inversion sequences can be repeated. So for example, if we take the sequence 0, 0, 1, 3, 0, 0, 6, 2, this contains a pattern 0, 1, 2. If I take this 0 and this 1 and this 3, the reduction of that is 0, 1, 2. I also could take this 0, this 1, and this 2. Or this 0, this 1, and this 6, or this 0, this 3, and this 6. It also contains 1, 2, 0. I could take the 1, 3, 0 and reduce that to 1, 2, 0. It also contains 0, 2, 1. I can find a 0, 2, 1 in here. E3, E4, E8, so 1, 3, 2. It doesn't have any copies of 2, 1, 0, which would be a decreasing subsequence of length 3. And it also doesn't have any copies of 1, 1, 0.
And just to make sure I'm on the same page here, it also avoids 0, 1, 1.
Yes.
Because the only repeated entries are zeros.
Right. That's correct.
Okay.
Okay, so we can define analogously consecutive patterns, which are just patterns that you require the occurrence of them, like the subsequence, to be consecutive. So basically, if you have the consecutive pattern, that means that you have a consecutive subsequence whose reduction is that pattern. And you can write down where the occurrences of that pattern appear. Since they're in order, you can just assign one index to each occurrence of the consecutive pattern. So if you don't have a consecutive pattern P, you avoid P. So here, this sequence contains 0, 1, 2. As a consecutive pattern, we can use this 0, 1, 2, or we could use this 1, 2, 3. It also contains the normal pattern 2, 2, 1, 0, but it doesn't have the consecutive pattern 2, 1, 0 because that would require it to have a decreasing subsequence of length 3. A consecutive decreasing subsequence of length 3. So we have a decreasing subsequence. We have 3, 2, 1 here, but we don't have a consecutive decreasing subsequence. Okay. So now we'll talk about equivalence relations for patterns. So we say that two consecutive patterns P and P prime are Wilf equivalent if the cardinality of the set of inversion sequences of length n that avoids P is the same as that for the set which avoids P prime for all n. So in this case, we use this tilde, so we say like P tilde P prime. They're strongly Wilf equivalent if for all n and m, the number of inversion sequences of length n containing m occurrences of P is the same as for the number of inversion sequences of length n containing m occurrences of P prime. So you can go from an inversion sequence that has m copies of p to an inversion sequence that has m copies of p prime. And they're super strongly Wilf equivalent if for any subset of 1 through n that I specify, the number of inversion sequences that have p at exactly that subset is the same as the number of inversion sequences that have p prime at exactly that subset. So this EMP prime, I think this stands for embedding from what I've seen in some papers. So like you can think of the embedding set of P and E as the set of indices where P occurs. And so if I give you a set of indices and I ask you how many inversion sequences have this pattern at that exact set of indices, it should be equal to the number of inversion sequences which have this pattern at that same set of indices. So in this case, they're called super strongly Wilf equivalent, and we use P tilde sub SS P prime. And so if you're super strongly Wilf equivalent, then you satisfy the conditions of being strongly Wilf equivalent, and you also satisfy the conditions of being regularly Wilf equivalent. And an equivalence of any of these 3 types is called a generalized Wilf equivalence. So in Juan Ali's thesis from 2020, he talks about these generalized Wilf equivalences, and he shows for all 75 consecutive patterns of length 4, he shows all of the generalized Wilf equivalences. And he also shows that among consecutive patterns of length 4, all of these equivalences are super strong. And they conjecture that this is true of consecutive patterns of length k for all k for patterns and inversion sequences. And so this is their theorem where they classify all of those equivalences. So there should be 75 total, but a lot of them they just have a single pattern in the equivalence class. So these are all the non-trivial equivalence classes. So basically all these patterns of length 4, you can exchange inversion sequences which have this occurring at some set of indices into an inversion sequence which has this this pattern occurring at that set of sequences. Or sorry, that set of indices. And so one way that they can show this, I guess we should look at this for a little bit longer. One way they can show this is if the pattern satisfies certain conditions, then you can literally just take an inversion sequence and you can take all the occurrences of your first pattern and just switch them over to occurrences of your other pattern. And as long as the patterns are like nicely behaved enough, then this will always give you a new inversion sequence which has the new pattern at exactly the indices of the old pattern. So what you would have to do is switch over the ones that look like this to this and the ones that look like this to this. And as long as they don't like coincide with each other and mess each other up, then you can just do this. So we'll talk about how those direct bijections work. So we're going to have to define some more stuff about consecutive patterns. So we say that consecutive pattern is non-overlapping if it can't overlap itself in more than one entry. So for example, the pattern 0, 1, 2, 3 can't overlap itself in more than one entry. And the pattern 0, 1, 0, 2 can overlap itself because you could have something like 0, 1, 0, 2, 0, 3. And so this would count, let's see. This is an occurrence of 0, 1, 0, 2, but this is also an occurrence of 0, 1, 0, 2. And these overlap in 2 entries. Yeah.
I have a question.
Mm-hmm.
So how, if 0, 1, 2, 3 is non-overlapping, but what about like 0, 1, 2, 3, 4, 5? Wouldn't that have it overlap at like at basically all sets?
Yeah, I guess what you're saying. Okay, maybe I should have come up with a better example here. So I think you're right, because you're totally right. If I did this, then you would have this. So this is not true.
Okay.
Let's come up with a different example. So let's see. We can just go back and look because I happen to know which of these things should work out. So how about 0, 1, 0, 0 and 0, 1, 1, 0? So we can try 0, 1, 1, 0. That one should not overlap itself in more than one thing. So in this case, you would have something like maybe 1, 2, 2, 1, and then you could copy that over, or you could do like, make these into 3s. And this one is actually non-overlapping because you can't make a new copy of itself that overlaps in more than one entry, because these have, in particular, this has to be like decreasing, this part has to be increasing. But yeah, you're totally right. This is increasing and increasing, so you could just overlap again.
Thank you. Excellent.
For pointing that out. Okay, so we say that two patterns are mutually non-overlapping if they can't overlap each other in more than one entry. So these guys should be non-overlapping with themselves, and they also can't overlap each other in more than one entry. I guess this is the same one we just looked at, but this one has to be increasing the first two entries. This one is decreasing the last two entries. And similarly, this one should be equal in the last two entries, and this is increasing in the first two entries. So there's no way you could write down a sequence that has these guys overlapping each other in more than one entry. And similarly, or sorry, not similarly, on the other hand, these guys are not. So for example, if you have 0, 1, 0, 2, 2, 3, then it has 0, 1, 0, 2 here, and it has a copy of 0, 1, 1, 2 here. So let's clear these. Okay, and then we say two patterns are interchangeable if you can always take an occurrence of P in an inversion sequence E and turn it into an occurrence of P prime while keeping E as an inversion sequence. So the way they define this in the thesis actually is they give you a set of conditions, like some inequalities that the entries of the patterns have to satisfy. And then they prove that if it satisfies that, that's if and only if with being with satisfying this condition. But I'm just gonna leave it like this so that we don't have to go through and talk about those conditions. So we can just say basically that if they satisfy this condition, they're interchangeable. So for example, if I had 0, 1, 2, 3, 0, I can't interchange that with 0, 3, 2, 1, 0, because 0, 1, 2, 3, 0 is a valid inversion sequence. But if I just change this into an occurrence of 0, 3, 2, 1, 0, now I don't have a valid inversion sequence, because 3 should be less than or equal to 1 in this case. So the idea for how to swap patterns where you have where they satisfy these three conditions. So if they're mutually non-overlapping and they're non-overlapping themselves and they're interchangeable, then you can just swap them. So this is how you would do it. So you take two patterns where I appears in P, if and only if I appears in Q. And so if P occurs in your sequence, then you have a consecutive subsequence S1 through SR whose reduction is P. So we can change the subsequence to one whose reduction is Q by just changing the ith entry in the subsequence to match the entry of P, which reduced to Q sub I. So basically you kind of line up which entries in the subsequence represented which entries in P, and then you match them up with what those should have been if it was Q instead, and you change them. So for example, I guess we'll go through this and then we'll go through this example. So if there are all three of these things non-overlapping, mutually non-overlapping, this would be bad, and interchangeable, Ali shows that their Wilf equivalence, he shows their Wilf equivalence to be a bijection which just changes all of the occurrences of P into P prime and vice versa. And the reason why you can do this is that you don't have to worry about them ever overlapping each other or overlapping themselves. And so this is a very straightforward map. You just have like some discrete sets of occurrences of each of the patterns, and then you just swap them. So in this case, if you have 1002 and 1012, and suppose this was my pattern, I have a copy of 1002 here, and I can just change it to 1012 by, I take the thing that counted for my 1, which is 1, and I make the third term of my subsequence into 1 instead of being 0. And then the thing that counted for my 2 stays what it was. So 3 stays 3, and the 0 becomes a 1. And everything else stays the same. This one, I also have a copy of 1002, and I also have a copy of 1012, but they're only overlapping in one entry. So I can still do this. So I have 1012, and then I change this 2 to a 0 because the 2 represented the 1 here, and I want it to represent a 0 here. So I copy it to whatever the 0 was. And then similarly, this one, I have a 0, 1, or sorry, I have a 1, 0, 1, 2 here, and I just change that into a 1, 0, 0, 2. So I can just switch them, and I will get a new inversion sequence, which gives me the set of p primes exactly where my p's occurred in the first place. And so this will show that they're super strongly Wilf equivalent. Let me remove these annotations. So this actually covers all of these green equivalences because you can show that all of these are non-overlapping, mutually non-overlapping, and interchangeable. And so you can directly prove all of these equivalences by just writing down this straightforward bijection where you swap the occurrences of p with p prime. So the rest of them, the ones that are left here, you can't directly do that because you have to worry about whether the patterns can overlap themselves. And so in that case, what they do is they prove a lemma using inclusion-exclusion that says if you have a map between like these other sets, then you can show that the cardinality of the actual set that you want is the same. And then they end up making maps for the other sets, but they don't get a direct bijection showing the equivalence. So I'll just explain what they do. So they use this inclusion-exclusion argument, and they say, suppose you have 2 consecutive patterns, and the cardinality of the set of inversion sequences which have p at a set containing s is the same as the cardinality of the set of inversion sequences which have p prime at a set containing s. So suppose this is true, and then suppose you have that for all positive integers n and for all possible s. Then you can show that they're super strongly Wilf equivalent because their proof, they just use the inclusion-exclusion formula to show that if this is true for all n and for all s, then you can show that these things are equal. And this comes from like the inclusion-exclusion sum. And so what this is saying is that if you have a sequence, and suppose I have p at like some set s, then I can go over and change my p's into p primes, and I will have p primes at s, but possibly somewhere else also. But that's still containing s, and so this is how I could get a map between these two guys. So using the lemma, the remaining equivalences can be shown as long as you have a bijection between these two sets. And to do that, you just need to get a map that will change occurrences of p into occurrences of p prime. And you might have some extra p prime occurrences somewhere else, but that's okay, because all you need is for this to contain s and for this to contain s. And so they say if you relax these conditions of being mutually non-overlapping, and you use the lemma to prove the result, he says this comes at the expense of not obtaining a direct bijection. But you can kind of recursively go through the maps and obtain a direct bijection by basically you write down a map and then you will go back and forth between these maps until you get the actual map that gives you the equality. So these are the remaining equivalences that we still haven't shown, or I guess that they're technically shown now by the lemma, as long as you know what the maps between these guys are. But we don't have direct bijective proofs of the equivalences, and so we will talk about how to get those. So for now, we're going to focus on 8 and 10, because these are patterns that don't overlap themselves, but they are not mutually non-overlapping. So for example, 1000 can overlap 1110. For example, if I have this sequence, I've got a copy of 1000 here with the 2 and the 1s, but then also these 3 1s and this 0 make a copy of 1110. So these are overlapping in 3 entries. So in order to define how I'm going to do this recursively, I'm just going to introduce some more notation. So for consecutive pattern P and a set T contained in 1 through n, we're just going to let I and P contains T to be the set of inversion sequences where T is contained in their occurrences of P. So basically, these are inversion sequences which have P at least the set T and possibly somewhere else. And then we define I and P equals T to be the set of inversion sequences where P occurs exactly at T. So we are interested in going between these sets. So we want to take an inversion sequence which has P at T and get another one which has Q at T, or P prime. And so if we have this map, which is the one, these should be reverse containment signs, but yes. So if we have this map, which changes the occurrences of P at positions T into occurrences of Q at positions T, then we can define this map recursively. So what we do is we take something which has inversions, which has inversion sequences whose copies of P are exactly at T, and we apply this map. So we change those copies of P into copies of Q. And then if we have more stuff than we wanted, so if we have extra copies of Q that aren't in T, then we will go back in the opposite direction and change all of those copies of Q back into copies of P. And then we'll apply this map again and change the original set of P's back to Q's. And hopefully at that point, we will be done and we will only have Q's where we wanted them to be. But if not, then we'll just have to keep doing this until we end up with Q exactly where we wanted it to be. So this S, I'm just saying this is the set of occurrences of Q in the result of this map. And if S is the same as T, then you can just stop because that's what you wanted. And if S isn't T, then we have to go through this recursive thing. And this like inverse, phi inverse equals S, this is defined recursively. So the way that this is defined is we would write it down the same way as this. So we would have to keep chasing through these maps until we got the actual equals map. Oh, wait, where did we go? Okay. Sorry. Which slide were we on?
Who's past this?
Yeah, sorry, I'm clicking through, but then yeah. Okay, we were here, sorry. And let me just go ahead and clear these annotations. So we're here. And then, so this is every step of the way, we're just using bijections. And so we should end up with a bijection when we're done. So for example, if my P is 1000 and my Q is 1110, then if this is my inversion sequence that I start out with, I'm just going to take this copy of P and I will change it to a Q. And I started out with P at position 3 and I ended up with Q at position 3. And so that's what I wanted, so I'm done. And to go the other way, I will just do the exact same thing, except now I'm going from Q to P. So I change my Q into a P and I'm done. If I have this sequence, I have a copy of P here that's also overlapping a copy of Q. So this might be a problem potentially, but what this ends up doing is it changes P into Q, and then my other copy of Q kind of got overwritten. So it's fine in this case. And so we started out with P at position 3, and then we ended up with Q at position 3. So we're done. And then going the opposite direction, you would just change this Q back into a P and you would end up here. So this one is a slightly more complicated example. Let me see how we're doing on time. Okay. So if this is my sequence, I have P at 3 again. And then I also have what looks like a looming Q over here, which might be a problem for me later. So I'm going to apply my map and I'm going to change my P at 3 to a Q, and I'm going to get this. So now I have a Q here, but I also have a Q here. And so I have Q at 3 and at 6. And so I need to compute phi inverse equals 3, 6 of the sequence. This should be a 6. So to do this, I'm going to apply the map that switches my occurrences of Q at 3 and 6 to P's. So I'm going to change this Q to a P, so I get 2, 1, 1, 1. And I'm going to change this Q to a P, so I get 1, 0, 0, 0. And so now I have P's exactly where I wanted them to be. I wanted them to be 3 and 6, and I have them there. And so this is the result of my phi inverse 3, 6. And so then I'm going to apply my forward map again. And this is going to be phi sub greater than or equal to T. So what that does is it only worries about the occurrences at T, which is in the set 3, or which is the set 3. So I'm only going to change my occurrence of my occurrence of P at 3 into a Q. I'm going to leave this other occurrence of P alone. And I end up here. So I changed this one and I left this one alone. And so I have Q exactly where I wanted it, which is only at 3, and then I don't have a Q here anymore. Let me delete these annotations. So going the opposite direction, what I'm gonna end up doing is just tracing back and undoing all the steps that I just did. So if I start out with the thing that I just got, I have a Q at 3, and then I'm going to apply the map, which changes this back to a P. So I get here. And now I have 2 copies of P at 3 and 6. And so I have to compute the map phi sub 3, 6. And this is, I guess, phi forward direction 3, 6, if I'm considering this to be starting with the inverse. So I change my Q's at 3 and 6. I change my P's at 3 and 6 back to Q's. And I end up here. And so then I apply my forward map again, and I change my Q at 3 back into a P. And I get this, which has P at 3, which is what I wanted. And it brings me back to what I started with in the previous slide. So this is how the bijection works. I think we probably have time for one more example. So for this one, what it does is actually, this is a more interesting example because you will end up creating like a new Q that you didn't initially have. So if you start with this, you have a copy of P at just 2. And then you change that into a Q and you get this. So now you have a copy of Q at 2 because you changed the P into that. And then you also have a copy of Q here, which is at 8. Then you have to compute this map. And so you change your Q's to P's and you end up here. So you had these. And this has P's where you want them. So you finish computing this equals map, and then you can apply the forward map again. And so you change this copy of P into Q once more, and you leave the rest of it alone. But now I have a new queue. I've made a queue at 6 now. And so I have to do this again. So now I compute phi inverse equals to 6, and I change my queues to P again, and I get this. And so I'm done. So finally, I can apply the forward map again at just 2, and I end up here. Any questions on this so far? Okay. And so like undoing that, you would end up kind of like retracing through those steps and get back to where you started. So the recursive way of doing this is complicated, and we wanted to see if we can write down a more straightforward way to do the same thing, because there's a lot of taking your copies of P and changing them to Q and then changing them back to P, and you're just going back and forth between P and Q at the same indices. And so if it's not overlapping, I claim that you can do it this way. You can take all your instances of P and just change them into Q. So you find your instances of P, and this is your set T. Then you're going to change all of them to Qs. And then if you have new Qs that you don't want, so you find a new set of occurrences of Q, and you compute like how many of those are not in T. So you have to find the set of Qs that you got that aren't supposed to be there. And then you just change all of those back to Ps. And then you just keep doing this over and over again until you have a sequence where T equals S. So for example, if I did the same, I think we had done this example recursively, but it's a lot faster to do it iteratively. So for this one, I had P at 3. And so then I change my P to a Q. And so now I have a Q at 3, 6. And so now instead of changing my 3 as well, I'm just going to change my 6. I change the Q at 6 back to P, and I end up here. And so I'm where I wanted to be, and I'm done. And then going the other direction, if I start here and I have Q at 3, I'm going to change that to P and obtain this. Now I have P at 3 and 6, and so I change the P at 6 back to a Q, and I end up here. And so I have the P at exactly 3, which is what I wanted. And I also end up back where I started. So the reason why this works, I haven't like included the proof here, but it's because the patterns, we require them to be non-overlapping, that we can just ignore the original copies of P, because the condition of being non-overlapping means that like we will not disrupt the existing copies of P by creating or by making changes. So like by making a change from P to Q or Q to P, you could create like some new occurrence of Q or P somewhere. And it might overlap with one of your initial instances of P. And that might end up making that initial instances of P or instance of P disappear. But the fact that we're requiring that they're both non-overlapping, this actually doesn't happen. And we can talk about that in more detail. I actually didn't really write it up, but I could discuss it more if that's unclear. Okay, so the remaining equivalences to prove are 1 and 13, which are these. So this equivalent and then these two equivalences. So these you can prove also by constructing maps which exchange the patterns, and then you apply the lemma, which is the inclusion-exclusion argument. And then by that argument, you can show that these are super strongly Wilf equivalent. But the maps that you write down, you have to be a little bit more careful, because these patterns can overlap themselves. And so in changing this to this, you might also change another overlapping copy of this into something else that you didn't mean to do. So you have to be a little bit careful with this. And so they actually write down what these maps are in the thesis, or at least they write down this one and they say that this one is similar, and you can see, you can like look at the map for this one and see how you would probably construct the other one. Okay, so the map which changes 0, 1, 0, 2 to 0, 1, 1, 2. Since 0, 1, 0, 2 can overlap itself in 2 entries, a string of overlapping occurrences of this pattern might look something like this. So this is what we saw earlier. And so to change all of these overlapping occurrences into overlapping occurrences of this, you could change it like this. So you can pull this 0 up to 1, and you can pull this 0 up to 2, and you can pull this one up to 3. And viewing these as under diagonal lattice paths, it's the same as just taking the second 0 in this occurrence of 0, 1, 0, 2, and making it match the height of the entry to its left. And the process of doing this is a bijection, which they show. And similarly, for the relation 13, you can write down maps which do something really similar for these. So you would just pull things up to match what they should be in the other pattern. And here is a diagram illustrating how you would do this for the under diagonal lattice path representation of an inversion sequence. So if you had something like this, you just take this and you push it up so they match. So again, you can still define a bijection recursively, and you do it the exact same way that we did before. So this one, this is the same map that I wrote down before. So you take the map that takes this set to this set, and again, these should be subset EQ, and you apply that map, and if you land where you wanted to land, then you're done, and if not, then you have to go back across in the opposite direction and keep going until you land where you want to land. So for example, if this is my pattern, then you would take this 0, 2, 0, 4, and you would change it into 0, 2, 2, 4. Sorry, I think this should be position 2. And then going back, the 0s 2, 2, 4 would be 0, 2, 0, 4. So, and then this pattern, you have a 0, 1, 0, 2 here, and you also have another lurking copy of this guy. And so you have P here, and then applying the map, which changes these occurrences, you will change that P into this. And then this part got ignored basically because you only changed the copy of P. So now you have two Qs, and one of them is here and the other one is here. And then you have to apply the inverse map. And if you change these back with the inverse map, you end up here. And this has P at 1 and also at 3. Now you apply the forward map again to just the original set, and you end up here. Does this make sense? Okay. So going back the other way, if you start here, then you have Q just at the first entry, and then applying the map, which changes Q to P, gives you back 0, 1, 0, 2, 0, 3, and now you have two copies of P, and then you have to go back along the inverse map, and you end up pushing up this 0 to a 1 and pushing up this 0 to a 2, so you're here. Now you have Q at 1, 3, and then you apply the forward map again, just to the original set 1, and then you obtain this result. So you end up at 0, 1, 0, 2, 2, 3. This one, 0, 1, 0, 2, 1, 3, has one copy of P. And then if you apply the map, which changes P to Q, you end up with 0, 1, 1, 2, 1, 3, which has Q at position 1. So we're done. We're not worried that we happen to have an extra P over here. And then similarly, you would take this and you would just map the initial Q back to a P in the other direction. So you might be wondering, is there a faster way to do this type of map?
Actually, sorry, could you go back to that last example real quick?
Mm-hmm.
So this final bullet point, we turned P into Q, and we have an additional copy of P,
Yes.
but we're not worried about it. We didn't initially have a copy of Q there, and so that's showing that this bijection is not an involution.
Right, I think. So I think like
This
if
turns
I
P's into Q's, but does not turn Q's into P's.
right. So if I try to take this and I send this through the map that turns Q into P, I will not end up here because this Q would turn into like 1, 2, 2, or sorry, sorry, this P would turn into 1, 2, 2, 3, which is not what it is here.
Okay, great. Thank you.
Yes. So that took a long time to go through how to do that recursion. And we would like to come up with a faster way that's iterative like we did in the other case. But these are a little bit trickier because they can overlap themselves and we run into some problems. So previously we wanted to just say, you take the initial instances of P, you change them to Qs, and then anything you didn't want, you just change back and forth until you're done. But if you try to do this for these types of patterns, you actually don't get a bijection. And I can give you an example of how this doesn't work out. So again, if this is your P and this is your Q, 0, 1, 0, 2, and 0, 1, 1, 2. If you try to replicate the same iterative process that we just said before on this previous example, then I would first change my 0, 1, 0, 2 into a 0, 1, 1, 2. And now I've got 2 overlapping copies of Q. And so if I wanted to just ignore the copy of Q that I like and change the other one back to P, then I would end up with 0, 1, 1, 2, 1, 3. So I just changed this copy of Q into a P again. So I do have Q only at 1, which is what I wanted. But if I do the same thing to this guy, so I have a copy of P here, and then I change that to a Q, and now I'm here. This has Q at position 1 as well, and so I'm done, but I've mapped 2 different sequences to the same sequence. So this doesn't work out to be a bijection if you try to do it straightforwardly in the iterative way that we did before. But we think that there is some kind of better interpretation of the recursive map that you can figure out, but we haven't actually done it yet. So these are the further questions that we are thinking about. So for one, we would like to have a nice description that's not recursive of what the map is doing when the sequences can overlap themselves. And then also, we would like to see how you can do this recursive approach for other combinatorial problems to find out new bijections. And then if you were interested in exploring more about like patterns and Wilf equivalences, you might consider, instead of just consecutive patterns, you could think about vincular patterns, which are just patterns where you underline part of the pattern. So you take like some subsets and you can underline them, which would require that underlined part to appear consecutively in order for that pattern to appear in an inversion sequence. So if your pattern is 0, 1, 2 and underline, and 0, 1 is underlined, then a sequence would contain this pattern if it has a copy of 0, 1, 2 where the 0 and 1 are consecutive. So this would be an increasing subsequence of length 3 where the first 2 entries are consecutive. So those are the possible future directions. And thank you for listening to my talk. Please let me know if you have any questions. Thanks.
Thank you, Melanie. So yes, questions.
So we have seen patterns of length 4. What about patterns of length 5? Have you tried some of these?
To be honest, I haven't really tried them, but I will say they have this conjecture that they said that this is analogous to another conjecture in permutation patterns. Let me see if I can find this. Yes, okay, so one interesting thing is that they conjecture that equivalences among consecutive patterns of length k are always super strong. And so it would be interesting to look into this and see, I mean, like, I guess the first step would be to look at length 5 and, you know, see if, I mean, I'm sure they've checked these for n up to some amount. But yes, I think that would be a really interesting thing to look at. But I think it gets more and more complicated as you make the patterns longer because they can overlap in many ways. So.
Thank you.
I have a few questions, but I guess the one to start out with is, so Wilf equivalences are when you do the pattern, the number of patterns are the same just on the permutations, not the inversion sets or the inversion sequences, right?
Wait, so your question is regular Wilf equivalences are on permutations?
Right. So these are generalized Wilf equivalences, but like there's a notion of Wilf equivalence for like the permutation pattern 213 or whatever.
Right.
Okay. And
I think
I guess my question is there any relation between these generalized Wilf equivalences and the Wilf equivalences? Like, are any of those?
I would be surprised if not. I mean, because like the inversion sequences are in bijection with the permutations. So be some relationships. And I wish I knew more about regular permutation patterns to like answer this question. But I think what you're saying sounds like it should definitely make sense. Like, I can't say for sure, but it seems like there should be a relationship between regular Wilf equivalences and generalized Wilf equivalences.
I guess the thing that comes to mind is like the easiest Wilf equivalences to prove is like the permutation pattern 1, 2, 3 and the permutation pattern 3, 2, 1 are Wilf equivalent because one line notation is symmetric, but that is not true of inversion sequences. And so like this is definitely weirder
Yeah,
in some sense.
I guess in this case, I mean, one thing you could, I guess, check, like you could convert those things to inversion sequences. Like 1, 2, 3 would become 0, 0, 0, and then 3, 2, and 0, 1, 2. And then I guess you could check those Wilf equivalences between inversion sequences, and then maybe try to like compose the map between the generalized Wilf equivalences with the map that takes you back to permutations.
Okay, yeah, no, it seems interesting. I have even less background. I remember the definition of Wilf equivalence. I was very proud of myself.
Okay, well.
Okay, so if no one else is chiming in, I didn't want to just, I often have like 7 questions. I think I'll ask one more during the recording. So if you have some of these patterns that don't have obvious bijections that you've covered, because they've got some they can have too much overlap between the patterns. And so if you just directly flip from one to the other, so 8 and 10 here, for example.
Right. So yeah.
Is there a notion of have you considered trying to figure out like if there's a finite number of ways they can overlap to try to find, say, a Wilf equivalent for the larger patterns, like say they can only overlap in 3 ways, then, and those are strings of 7 characters or so. Could you find a Wilf equivalence for the 7 character patterns and then that go back down to the 4 character patterns? Is there a way of kind of like kicking this up several levels and then coming back down?
So if I'm understanding your question, you're saying like, let's suppose that we have something where these guys overlap, like something like this, and then you're like, well, let me just think about this pattern.
Yes.
That's an interesting question. I have not thought about that, but I feel like that should maybe do something. I think when I was initially thinking about this bijection, I was like, well, these are the only ways that they can overlap, and if you apply the map, then this becomes something else, and then you're done. But the only thing is, applying the map to this, you can still create like other peripheral copies of things, I think.
Okay. So like, maybe the big map doesn't give you equivalences for the smaller maps, but the smaller maps might give you Wilf equivalences for the bigger map.
That might be the case. I mean, I'm not 100% ready to say that what this, like doing it with the bigger map first, like wouldn't work.
Yeah.
For this one, if I changed this, like if I was going P to Q, then I would do this. But then like if I had a 3 over here, I could have like another copy of P that crops up. And so then you'd still have to worry about like overlapping with some other thing.
Right.
Yeah. But that's a really interesting idea.
Okay.
Thanks.
We have a lovely comment in the chat. Oh, no, that's a question. That's are there, not there are. So reading the comment in the chat for the recording, are there nice closed formulas for the number of permutations with inversion sets that avoid these patterns?
I think there are, and I think that at least some of them are in Juan Ali's thesis, which I will scroll to that slide so you guys can see the title and everything. So I haven't actually looked into this very much myself, but I think at least for like shorter patterns like length 3 and stuff, I think there are some nice formulas, and I want to say some of them are like, well, okay, I don't want to say anything that I don't know if it's true, but I want to say yes, there are nice closed formulas, or like you can like write a bijection between the inversion sequences which avoid something and like some other thing, and then you can show it's counted by this. So yes, I think so.
Okay. I think that's a good place to stop questions for now. Let's all thank Melanie again.